my examples for the regiochemistry were off. So on this packet, on the back side where we had the reaction diagrams, I want you guys to reiterate from what I said. What is the distinction between the starting materials highlighted in the top two diagrams? One is a terminal alkyne and one is internal. It's within the carbon chain. This one? Yeah. Alkynes, nomenclature and reactivity. Is that what it's called? Do you see it? Under Module 5, Unit 5. Alkynes and radicals, sorry. So, why did I do this? Actually, let me phrase that differently. I did this to highlight the regiochemistry of some of these reactions, like Markovnikov or anti-Markovnikov. Which of the alkynes, terminal or internal, highlights regioselectivity? The terminal alkyne, because it has different substitutions, different regions. So, for example, here is cyclohexyl acetylene. Yeah, 1-cyclohexyl ethyne. What happens if I react this through hydroboration oxidation? What functional group should I form? An aldehyde. So here is the terminal carbon. I'm going to call that 1, 2, and then by 3 I should be at my cyclohexane. That terminal carbon, aldehydes are terminal. They are also sitting at the end of a functional group, or the end of a carbon chain. So here I get 1, 2, 3 puts me back on the cyclohexane. I don't practice drawing my cyclohexanes sideways very often, so it looks a little funky. What happens when I have 1, 2, 3, 4, 5, 2,5-dimethyl 3-hexyne, and I react it the same way, hydroboration, oxidation? What functional group do I get? I can't make an aldehyde, can I? There's no terminal carbon. I know that this is an anti-Markovnikov hydration. I know that it will add hydrogen to the more substituted carbon and oxygen to the less. But this does not have a more substituted and less substituted carbon. So I'm screwed? Does this reaction just not work? Does hydroboration and oxidation only work with terminal alkynes? What would it do if it reacts with an internal alkyne? How would it know where to put the H and the OH? It doesn't matter. So one of these carbons becomes the carbonyl and one gets the 2 hydrogens. Earlier, I was specific about it. The terminal carbon gets the carbonyl because I need to form an aldehyde. Here, it doesn't really matter. Well, and this was a symmetric molecule anyways, right? So whether carbon 1 or 2 of the alkyne became the carbonyl carbon, I would have gotten the same structure no matter what. What happens when things go a little bit differently? Now we say that the oxymercuration hydration reaction is Markovnikov anyways. Which carbon of the alkyne is more substituted? The carbon on the left, which is bonded to a carbon, or the carbon on the right, which is bonded to a carbon? No difference. Salem, I saw you nodding here because this is a tertiary carbon, right?
Yeah.
But I'm not asking if this carbon is more substituted than this. I'm asking which of these two carbons is more substituted. And they're both bonded to one carbon. They have the same substitution. There is no regio difference. But there is a regio difference. The carbon on the left is closer to cyclopropyl. The carbon on the right is closer to ethyl. Do those make an impact? No. It just means that I have an unsymmetric alkyne. And an unsymmetric internal alkyne can yield two different hydration products. What if carbon 1 becomes the carbonyl? What if carbon 2 becomes the carbonyl? Those are structural isomers of each other. So we saw this come up with alkene addition reactions too. Sometimes alkenes do not have a more and less substituted carbon. Sometimes both carbons are equally substituted. And yet they are regionally different, so depending on either possible product, I get structural isomers.
Do you have to put both if you're like writing the product?
Yeah. Yeah, and so that becomes tricky in a how do I ask you this kind of way. Sometimes you'll see this as this starting material has two products, one is shown, what is the other? Although you guys know how to get around that. You just say, no other products form. Usually when I am asking that, I'm not trying to be tricky. I'm just, but I do think, I sometimes don't clarify the confusion between byproducts, major organic products, and minor organic products. Sometimes reactions form mostly one thing with a little bit of another on the side. I think early on when I'm introducing you guys to organic reactions, I could probably do better at defining the difference between byproduct, major product, minor product. Sometimes they're not always clear though. Those definitions are a bit ambiguous. Okay, so I highlighted different degrees of substitution so that I could highlight how some of these reactions really do depend on regiochemistry, but I did not actually align those reactions well. So yeah, let's just recall the ones that I screwed up. I showed this happening. Except that I showed the product for this happening. In fact, I don't always highlight that H, so I don't want you to get confused that I might always show you that. So I gave this starting material, wow, that was funny, and this product. And that was my fault. I was trying to highlight the Markovnikov feature, but I did it on a reaction that doesn't have Markovnikov versus anti-Markovnikov. So this is what I had wanted to give you. And then similarly, I screwed up with the 2x addition, which means that I really had just wanted to flip those with the x2 addition, because x2 is not regio-specific. X adds to both carbons. Yeah, all the confused scowls I see tells me I messed up in all the ways I needed to. All right, are you guys interested in seeing some of these mechanisms? Okay, close your eyes, Britton. I want us to compare some of the mechanisms that we already know to the mechanisms that you're not going to be tested on. So I'll be clear with that. The alkyne mechanisms are not ones you'll have to draw, but you already know how to draw them. Let's take 3-methyl-butyne, and let's run it with HX addition, HBr in excess. Until we get 2,2-dibromo 3-methyl-butane. When we ran this reaction with simple alkenes, I had you guys analyze the situation a little bit. I told you what the first step was, but I wanted you to analyze the reagents. What type of reagents do we have present? A lot of answers here. This is very open-ended. What type of reagents are present? An acid is present. What else? Britton, how'd you know it was an acid? Yeah, it's hydrobromic acid. Good. No? Generally, if there is an acid, then there is a base. What would be the base? The alkyne must be the base. Was that true in our alkene addition reactions, that the alkene was the base in the presence of an acid? Sure was. Our first step of HX addition, do you guys remember? What was the first step in that mechanism? Acid base. Another way that we could call it is protonation. Protonate the organic compound. Okay, some other correct answers that you could say here is I have an alkyne. I have a terminal alkyne. And the idea that I have a terminal alkyne is useful because that actually tells me that I have some partial charge chemistry. More substituted, more willing to let go of the electrons of the alkyne pi bond. Less substituted, more likely to hold on to the electrons from the pi bond. More likely to use, more likely to lose. And remember that my charges line up opposite. So my partial negative is attracted to my partial positive. That's my acid-base chemistry. So my first step is acid-base. True or false? In the alkene HX addition mechanism, there was a carbocation formed. Take a few more seconds. Think about it. In the HX addition of alkenes, is there a carbocation formed? Does it depend? Raise your hand if you believe there is a carbocation formed. If you think it depends, or if you think there is no carbocation in the HX addition mechanism. What do you guys need to study? Study that HX addition mechanism before the final where you see it and have to draw it. It's so fun to draw them, though. The answer is yes, always. But there is sometimes a carbocation rearrangement. The rearrangement depends. This agrees with a carbocation forming. A carbon-carbon pi bond breaks, but only one of them is bonding to something new. That means the other carbon is going to completely lose those electrons. Where is a carbocation more stable? Say that again? Did I hear some less substituted? Okay. More substituted, more stable. Yes?
I just want to make sure that I am understanding this. Right now we're going over the section of radical reactions, right?
No, sorry, we're kind of wrapping up. I wanted to talk about more of those alkynes.
Okay. So I was like, I'm not seeing this on that section.
Correct.
But I'm also seeing the disagreement of this on that section. So I wanted to clarify.
Yes, well, I don't have reagents on that last diagram.
Yeah, which is part of why I was like, if that is what it's supposed to be.
Correct.
Then
No, we're doing the HX on the reaction above. Essentially this, but
just
it,
a different example. Okay.
yes.
Just
Oh, you're right. Actually, I didn't even realize I used 3-methylbutane for that. Good eye.
that's why I was confused, because I was like, I'm seeing
Seeing the same starting material, but it's not going in the right direction.
No, it's not.
What have I forgotten here in my intermediates? The carbocation. Where is it? The carbon to the left. I have just created a CH2 from a CH. Why does it have that geometry? Why does it look linear? What hybridization does it have? It was sp hybridized. It's still sp hybridized. Does this remind you guys of anything, by the way? What's the next step in this mechanism? Carbocation rearrangements won't happen here. This is not a normal carbocation. Now, nucleophilic attack. And all of a sudden, I don't have an alkyne anymore. I have an alkene. Oops, but I did forget my bromine, didn't I? Does this remind you of anything?
I know.
Oh,
I don't know, but I know. It's from our other ones.
yeah? How many of you have done your midterm analysis assignment? You recognize this? This is the mechanism I had you guys do on the midterm. I gave you guys the arrows. No, I gave you guys the intermediate and I had you draw the arrows. A lot of you nailed that step. And then I gave you guys the arrow for the second step and had you determine the products. And that's where a lot of the misunderstanding of arrows showed up. But this is actually a mechanism I've already shown to you without you realizing what you were looking at. I did that on purpose. I wanted to throw you off the deep end a little bit early on so that when you come to the deep end, it's familiar. Obviously not super familiar because you guys don't remember it. So what happens here? I have an alkene and I have an acid. Well, if I have an acid, I must have a base. So let's do an acid-base reaction. Now you might say, put the carbocation on the most substituted carbon. That's true, but I also know that the alkyne always gives a geminal dihalide product, never vicinal. Two equivalences of HX will always give a geminal product, which means that my carbocation really forms on the same carbon as last time. And then my nucleophilic attack happens to the carbocation. And I can validate that nucleophilic, or I can validate that carbocation better than any other, because that carbocation actually has a resonance contributor. It's not a very good resonance contributor because bromine doesn't really want to share its electrons all that well. But this resonance contributor maximizes octets. Every atom has a maximized octet here versus carbon lacking an octet with the carbocation. So this is a better resonance form. And technically, it is this resonance form that enables this carbocation to form so well. The resulting geminal dihalide is because this carbocation forms no matter what. Okay, so you guys know that mechanism. And now you know how to do it essentially times 2. Start with an alkyne, you get 2 equivalents worth of HX. I wanted to take a minute to look at the X2 addition as well. Who remembers the first step of an HX addition, of an X2 addition mechanism? It's not as easy when I don't have an acid and a base. So this is a mechanism that if you don't recall it from alkenes, keep reviewing it, because this is a mechanism you can see on the final where you have to draw one. Not for the alkyne, but for the alkenes. First step here is the halonium ring formation. So the alkyne attacks one of the halogens, the halogen attacks back, and a halide is kicked off. There's my halonium ring. Although, to be fair, that's a really weird halonium ring. The last time we made a halonium ring, it was alkene, double bond, to halonium ring, 3-membered ring. But now it's from alkyne to alkene halonium ring. It is a super strained intermediate. And then, what happened with our alkenes? Backside attack. The nucleophile opens the halonium ring from opposite the carbon-chlorine bond, the carbon-halogen bond. How does the stereochemistry of this one equivalence product prove to us that the mechanism is including that backside attack? If the 2 chlorines added to the same face of the alkyne, they'd be right next to each other on the alkyne. Or sorry, they'd be next to each other on the resulting alkene. One of the chlorines added to one face of the alkyne, the other added to the backside, which is why our one equivalence addition is a trans dihalide. Now what functional group do I have? Alkene. Simple. We know the mechanism for this. Pi bond attacks a halogen attacks back, a halide is kicked off. The halonium ring forms. And the halide that results does a backside attack. Here, it really doesn't matter where anything gets attacked because I end up creating 2 achiral carbons. Always. Fun, fun, or scary, scary? It's very fun. These are all mechanisms you know. All mechanisms you've done on your unit test. Well, no, yeah. I asked you guys to know the acid-catalyzed hydration as well, but the acid-catalyzed hydration doesn't really exist for the alkyne. There's just the oxymercuration or the hydroboration oxidation. All right, there are 2 more reactions that I want to show you, and one of them will help us segue into the radical chemistry at the bottom of this worksheet. The first is, how do I take this alkyne and use Lindlar's catalyst to create a cis-alkene? First, this should prove to us that hydrogenation is syn addition. The 2 hydrogens added to the same side of the alkyne. That's why the 2 hydrogens are on the same side of the alkene. I do disagree with some textbooks that show the mechanism for this, but inside of Lindlar's catalyst, there is palladium. That's what you guys are working with this week in lab. And that palladium uses some of its d orbitals to interact with the antibonding molecular orbital of hydrogen. It takes H2 and it breaks the bond. And this is our palladium down here. It's palladium's d orbitals. Okay, the way that it makes sense to me to represent this is to show hydrogen held onto by palladium, because that is essentially what it will do. Another way that you can represent this, though, is to show individual bonds between palladium and hydrogen. That's what some people show. Then the alkyne approaches. Same thing happens with the alkene, and there is a movement of electrons. The reason that I like to show it as molecular hydrogen is because the movement of electrons makes more sense. Here the alkyne donates electrons to 1, while the other hydrogen donates the shared electrons to the other carbon of the alkyne. And so this stick, the alkyne, picks up 2 hydrogens at the same time and gets forced into a cis-alkene configuration. Why doesn't it just do it again, though? More hydrogen comes onto the palladium, and then the alkene sits down on the palladium. We already know alkenes do that. So why doesn't this alkene react with more hydrogen on palladium? Lindlar's catalyst is a poison. It has quinoline and barium carbonate, neither of which I have ever seen an explanation as to how they poison it. But Lindlar's catalyst poisons this alkene, making it unreactive to the palladium on hydrogen. We already know that we can take alkenes and that we can use hydrogen and palladium and reduce them to an alkane. But this alkene will not, and that's because of Lindlar's catalyst. Okay, so we learned that this is one way we can partially hydrogenate an alkyne. If I wanted to fully hydrogenate the alkyne, I would just use palladium. I wouldn't add in the rest of Lindlar's poison. But I can also partially hydrogenate an alkyne by metal ammonia reduction. Sodium is a common metal to use here, but you can also use lithium as a metal. And sometimes you will see this clarified as liquid ammonia. So this is happening with high pressure. To get liquid ammonia, you need higher pressure. And this gives us what type of alkene? A transalkene. So the mechanism must be different because the stereochemistry of the resulting alkene is very different. Was it obvious where the hydrogens came from up above? How did those hydrogens get onto those carbons? They came from H2. Where do the hydrogens come from here? They must come from NH3. That's the only place that has a hydrogen. So I actually need to create a base on my alkyne so that I can deprotonate ammonia. Does that seem fair? So I need to figure out how to make a base. This is where sodium's role comes into play. And I'm actually going to, I'm going to keep track of all of my equivalences throughout this mechanism. I'll need 2 equivalences of sodium and 2 equivalences of ammonia. Do you notice what I drew over the sodiums? I drew a what? A radical. Why? Because it's not an ion. If it were an ion here, it would need to have its charge, or it would need to have a counter ion. But there's no counter ion. Ammonia is neutral. There's a comma after sodium. This is elemental sodium. And how many valence electrons does elemental sodium have? Just 1. And it doesn't like to hold on to it very much. It likes to give it away. So elemental sodium gives an electron to one of the alkyne carbons. That alkyne carbon already has enough electrons. So in order for that electron to be received, a pi bond must break. There are 2 things that can happen here. I form a radical and an anion. Would you guys agree that that is what makes sense from these arrows? A radical forms, and one of the carbons takes a pair of electrons. I form a radical and an anion. Or I form a radical and an anion. With what distinction? Cis versus trans alkene. The way in which my unpaired electrons arrange themselves in space can also dictate the way in which my carbon chain is arranged in space. So which of these is more energetically favorable? And why? So what are you going off of to say this must be more energetically favorable?
When they're on the same side, isn't it bad? I don't know.
When what are on the same side? The carbon chains?
The charges.
The charge. Well, I've only got one charge.
The charge and then the radical.
So my unpaired electrons being on the same side would be unfavorable. Anybody want to add to that? Give it a name, a reason why? Comes down to valence shell repulsion theory, Vesper. Valence shell electron pair repulsion theory says, well, first of all, that is the explanation we give you in Gen Chem for why molecular geometry happens in the first place. Why is a 4-electron region atom tetrahedral? Because that allows its electrons to spread out as much as possible. And why is water's bonding angle smaller than expected? Because the lone pairs on water repel each other more greatly than the bonding pair of electrons repel each other. And it's the same here. The non-bonding pair of electrons repel each other more greatly. So we never see this electron repulsion because it prefers to form anti to each other so that they don't have that electron repulsion. So we know why we get a cis-alkene from hydrogenation with Lindlar's catalyst. It's because the palladium plays a role in holding on to the hydrogen for the alkyne to settle on it. We also know why hydrogenation with metal ammonia is trans, because when the electrons form in this first intermediate, they want to be as far away from each other as possible. Look at balancing charge. I've just created a negative charge. What should I balance this with? A positive. Where have I formed a positive charge? The sodium that just gave up its valence electron. I also still have another equivalence of elemental sodium. And now I'm going to highlight how ammonia plays a role as an acid. It has to be my proton source. So my newly formed carbanion acts as a base. Okay, again, I'm not showing that hydrogen. Does that mean that I don't want you to show that hydrogen? Then why don't I just draw it? Like, it feels like I'm not setting you up for success if I'm just not drawing it. I can draw it. It's not hard. You can draw it too. In fact, you can draw every single hydrogen on every molecule you ever see. Don't assume any of them. Draw them all in. It just takes a long time, and after you draw about 100 of them, you'll realize why we don't draw them all. And the reason that I'm not drawing it here is because I want you to feel familiar with this as well. I want you to be able to interpret that as a new hydrogen. So what happens next? I form a byproduct of sodium amide. That is Na plus and NH2 minus, unlike Na, NH3, which are neutral. I'm not going to redraw that byproduct anymore. That is just a waste byproduct. But now I have a radical, and those can come together to form a new anion pair, a new sodium ion, and set me up for my second acid-base proton transfer. When I TA'd OChem 1, that was fair game for a mechanism question on the final. Which was fun because that was the first time I learned it, was TAing it to the students, and then they had to be expected to know it. I didn't have to though. I just had to grade it. Anyways, I think it's actually really easy when you think about it, but a lot of times this stuff is just not thought of very well. What do you think of it? What a cool combination of radicals, negatively charged carbons, change of alkyne to alkene. And here's another question. If an alkyne reacts with these reagents, why doesn't the alkene? Right? How come I can't have more sodium react here and form yet another radical anion pair? Well, the alkene is just not as reactive as the alkyne. The alkene is more stable. So getting this to react in a similar way is just much harder. All right, on the note of radical reactions, the last reaction diagram all involves radicals. And we'll look at some of their mechanisms, but once again, they won't be ones that you have to draw on the final exam. I do want you guys to feel familiar with these intermediates. I want you to understand the process of how the reactions transform. But in terms of drawing them, you won't be graded on it on the final. This semester. Future semesters, I don't know, watch out. That was to the camera, not to anyone over there, sorry. Okay, you'll notice in this diagram that I have a few different starting materials. Is that clear? The alkyne is shown in two different reactions. The alkene is shown in two different reactions. Let's start with the alkane. First of all, you might just swap out that X for a BR, because we aren't going to do this reaction with anything other than BR. Why didn't I think about that? I don't know. Ask my manager. The reason is, when you try to use chlorine in this type of reaction, chlorine is too reactive and it can't be controlled. But bromine is reactive enough that we can control it. Our reagents here. Well, first of all, what change am I doing? What type of reaction? Is this addition, elimination, or substitution? What am I substituting? I'm not consuming a pi bond, so it's not addition. I'm not creating a pi bond, so it's not elimination. I'm substituting that hydrogen. So we call this radical halogenation. Specifically, this is radical halogenation of an alkane. I need to abstract a hydrogen. I need to get a hydrogen out of there so that I can put my bromine in. So I use Br2 and H-nu. What's another word that I could use to replace H-nu? Light. Those of you that used bromine in last week's lab might be the last semester to ever use bromine here at Slick. We're going to get rid of it. It's dangerous. It oxidizes everything. It's crazy oxidative. If in that 280 lab, there's a whole cabinet we used to store it in, and the inside is just rust. Except for the tub, where the tub sat that held the bromine. Everything else is just totally rusted. So we're going to get rid of bromine. So you guys might be the last people to ever use bromine here at Slick. And you might have noticed that it was stored in those brown glass bottles. That is to prevent light from getting in, because light will turn bromine into radicals. So I like this mechanism. I'd like to go through it with you guys. It highlights all of the key points of a radical mechanism. The problem is I actually have a worksheet that has these steps. I just didn't give it to you. So I'm going to lay out what these steps are. Radical mechanisms follow 3 steps. The first we call initiation. That is, no radicals exist. We create radicals. In this case, that means light activates the electrons in bromine and causes homolytic cleavage. The 2 bromines split into 2 bromine radicals. What do you guys understand propagation to mean? Any botanists? Oh, it's okay. Regrow. Take and grow. Yeah, that's how I understand propagate with my plants, but that is not what we mean by propagate in radical electrons. Propagate in radicals means one radical reacts with a non-radical and produces a new radical. I don't multiply, I just transfer. So this maybe should have been called a transferring step than propagation. There's other people that you can take that up with. All right, we have to consider where our bromine radical will react with the alkane in order to leave a new radical. Where is the most stable place? Which position requires the least amount of energy to form a new radical on? The most substituted. Because there's nothing allylic, there's no resonance of my radical that I can create. This is the most substituted, which is very similar to forming what other type of intermediate? Carbocations also prefer to go on the more substituted carbon. My most substituted carbon here is the tertiary carbon. So it is that hydrogen that will be abstracted by the bromine radical. Here's what that looks like. Bromine radical forms a bond with the hydrogen, 1 electron from each. The CH bond then also breaks to the carbon. Homolytic cleavage is awful because it requires us to draw the most arrows. But notice how this leaves a carbon radical on the tertiary position, and it gives us a byproduct, HBr. The last type of step that can happen in radical reactions is called termination. How would you describe what you think termination is going to be? Initiation, no radicals become 2 radicals. Propagation, 1 radical becomes a different radical. Termination. No more radicals. 2 radicals combine and leave no radicals. So in this case, it is my bromine radical and my newly formed carbon radical that come together and give me my new alkyl halide. That's my major organic product. How very fun. So I want to say something about alkanes. This is the one and only reaction that we'll learn about with alkanes. There is something else that you can do with alkanes. You can burn them. That's how a lot of us get around every day. It's how a lot of us heat our homes every day. Burning natural gas, burning octane. I actually would not be able to draw you an electron arrow pushing mechanism for combustion. I don't think I've ever seen a mechanism for combustion. So if you're interested, you should try it and show it to me. I'll give it a look. The only other thing that we can do with alkanes is halogenate them at the most substituted carbon. So there will be reactions later in the semester where you are asked to solve a synthesis that includes multiple steps. And if you start with an alkane, great, super easy. There is one thing to do with it: Br2 and light. The reason that we don't react with Cl2 and light is because Cl2 will not just go to this most stable position. Cl2 is reactive enough. It doesn't take a lot of energy for Cl2 to halogenate at primary and secondary positions, especially when you consider how many primary hydrogens there are. For a chlorine radical, there's 9 chances to 1 that it reacts at a primary carbon instead of a tertiary carbon. So radical chlorine, too reactive for us. Radical bromine, just in the sweet spot that we get the regioselectivity from it. Okay, why don't you guys take a 5-minute break. Let's come back at 6:05, and we'll look at the rest of our radical reactions.
What's the pass rate for your class?
Oh, no one's ever asked me that before. What do you expect it is?
I don't know. 80?
What do you mean by a pass rate? Like, what's the cutoff for you? C and above? And you think I have an 80% pass rate? Take care. Oh, Hamza, do you have time to stick around and answer that question? On active?
Yeah.
I meant to do that. If you have time, we can do it right now.
Sure.
Do you have to go?
It's okay. Yeah, I can in a bit.
Okay, let's look at it. Said it was section 9, question 13. Okay. So you said you tried, what, a geminal dihalide and a vicinal dihalide?
Mm-hmm. And it didn't work.
Do you want to try drawing one for me? Show me.
And it doesn't work in terms of it had like I don't know, like 2 branches out of like the carbon, so I can put like 2 chlorides.
Mm-hmm.
So and it's I just like it's not in the program, just like it's not coming out. Do you want me to just draw it and try to send it to you?
Do you feel like you can't draw it right now?
It's just like in the program, it's just like I don't know like how to explain it. Like it's not
So
making me like do 2 of them. Just
do you want to, here I can add a chlorine, right?
okay.
I want to add another chlorine. I just need to draw a new bond and then change that bond to go to a chlorine.
But it actually was really helpful.
And that's it.
Now I've got 2 chlorines on the same carbon. This is not your final answer though, because I don't have enough carbons.
So
So
like add another chlorine to that bond, right?
But it helps because there's just
No.
so much information.
So I want benzene 1, 2. Benzene 1, 2.
Okay.
And then I want to have 2 hydrogens removed and 2 halogens removed. I can modify this. And I can have, here's benzene 1, 2. I can have a chlorine come off of this carbon as well. I went from having a geminal dihalide, now I have a vicinal dihalide.
Okay.
And I could have another geminal dihalide on carbon 2 instead of carbon 1.
Okay.
But I think maybe you were trying to get it to say Cl2 with a subscript.
Yeah.
Cl2 is a molecule in and of itself, Cl to Cl.
Okay.
So I don't want a bond that goes carbon to Cl to Cl. I actually want 2 Cls bonded to the same carbon.
Yeah, that's what I was trying to do. I don't know.
Take a screenshot once you get to it. If it doesn't let you submit again,
Yeah, I'll try and then I'll send it to you.
okay,
All right, thank you.
you bet.
We could have done better. Singing? I don't know, bro. Don't piss me off right now. Why is it doing that? I didn't want to go into it. I hate when it does that. Okay, class schedule for summer. Do you have your wedding planned?
Mm-hmm.
When is it? Is it in June?
It is.
Oh my gosh. Summer wedding. Is it gonna be here?
Yeah, in the big Cottonwood Canyon.
It'll be cooler.
It will be. Yeah, in fact, we just got like 2 feet of snow up there in April, early April.
Oh, perfect.
And I was like, okay, it's got 2 months to melt. Actually, 2 months from today.
Scott. I think I know who that is. I don't think she teaches here anymore though. Who's my I believe in you. I also believe in myself. I'm just gonna go to law. But it will be okay. It's only 4 weeks. That makes it so much harder. I took quiz 2 over the summer. You took physics 2 over the summer? Yeah. How was it? I just feel like what our normal semester is 14, isn't it?
All right. 16.
Oh, it's,
Normal semester is 16.
am I gonna die? Am I gonna die in this house?
I think I'm gonna die in this house. What are you taking this summer? That's doable.
Okay.
Anything more than that,
You think I can do it?
very much not doable. Yes. Did you know that you have nearly the same amount of time in class during the summers? You miss 4 hours of class during the summer compared to the fall and spring. And it depends on your section days as well, like what holidays you have. You know how we missed 2 lecture periods early in the semester?
I just have Tuesday, Wednesday, Thursday classes, so I don't think I should miss any. Unless
I think you might be right. I think there's no holidays.
Fourth of July's on a Friday.
There is a Thursday holiday. The 4th of July is a Friday. Pioneer Day is a Friday. Oh, Juneteenth, I think, is a Thursday.
Isn't that June 19th? Yeah.
On the slick,
Oh, but maybe they.
On the slick academic calendar, they reported June 19th as a holiday this year.
I think that there's oftentimes like observed
They did that?
days.
They're observing it June 15th. What is June 15th?
Monday.
Oh, okay. Yeah, then there's a Monday holiday.
They should know this. Wait, I didn't realize it. Guys,
All right,
don't worry about it. Nothing you
you'll survive it. People survive all the time.
yeah.
Actually, some people barely survive taking calculus in addition to physics and OChem.
Oh,
But physics and OChem is, are you working?
yeah. Part time. Not full time. I'm going to part time.
Yeah, just know your schedule. Plan ahead. Any calc. Calc 2 is the hardest.
That's true.
Calc 3 is a breeze.
It's when you go to Linde.
Calc 3 is, if you can get through Calc 2, Calc 3 is super easy. All right, which way do you guys want to look first? You want to look at the alkenes or do you want to look at the alkynes? Okay. Alkenes. I've got one alkene and two very different reactions. First, can you tell me a little bit about this alkene? It's terminal. We actually have more than one type of terminal alkene. For instance, here is another terminal alkene, and they have differences between themselves. So terminal's not bad. What more can you give me? What is the substitution of the alkene? When you describe the substitution of an alkene, you describe both carbons comprehensively. And we use different terms. Rather than primary, secondary, tertiary, quaternary, we use mono. This is a mono-substituted alkene. Good. Which means that it has regiochemistry. It has a more substituted and a less substituted carbon. What do you notice about the two reactions coming from this? Do they give the same end product? Do they give the same functional groups? Tell me a difference you spot.
Between those two,
Yeah, between the products formed from the same alkene.
there's one that has an alkene still and one that does not.
Good. One consumes the alkene. What type of reaction consumes a pi bond? Addition. One does not consume the alkene, so what type of reaction must it be going through? This is substitution. That substitution up above provides not just an alkyl halide, but an alkyl halide that is adjacent to an alkene. Do you remember what term we use to describe a halide adjacent to an alkene? Or anything adjacent to an alkene? Allylic. So I can form an allylic halide from an alkene by doing substitution. Boy, that sounds a lot like forming a most substituted halide by doing substitution on an alkane. I'm going to use the exact same reagents. In fact, if you wanted to, you can swap out these X's for BRs because we're not going to do anything other than BR2 and H nu. Okay, well, earlier we said the alkane selectively forms the tertiary alkyl halide. Why does this one form both a tertiary and a primary allylic halide? In the mechanism, the bromine splits apart just as before, but now the most stable radical is not just a tertiary carbon. The most stable radical is the allylic carbon, which just so happens to be tertiary. So by the time we get to propagation, I have what looks like a very similar radical to my alkane reaction. A tertiary radical, although this time it's a tertiary allylic radical. Does that radical even exist? I feel like that lady on the plane. That person back there is not real. What did she say? That's how I feel looking at that. Oh, she swears, doesn't she? That motherfucker back there is not real. And it's true. This molecule does not exist. Does anybody agree with me on that? Do you just take what I say at face value and go home? Why is it not real? Because our little kindergartner minds in the reality of the universe can't comprehend resonance super easily. And we certainly can't comprehend a structure that has two different resonance forms. Allylic radicals are more stable than any other radical. They're not the most stable. Benzylic radicals are more stable. Allylic is more stable than non-allylic radicals because they are resonance stabilized. Can we backtrack? Do you know why the radical is so reactive? Radicals are not things you really want to deal with. That's why in your body you have things that take care of free radicals. Do you know why radicals are reactive? They're magnets. They're actually unpaired magnets. That electron spinning creates a magnetic field that wants to pair with another spinning electron. So radicals are reactive because they're little magnets looking for a pair. If I can spread out where that little magnet is, I can stabilize it. I can make it half a little unpaired magnet at two different places. And I do this unintentionally because there is a three-bodied system of p orbitals, and that middle energy orbital holds my radical. That radical is not on one carbon or the other. That radical is on both of them. So when I form my allylic radical, there are two possibilities that happen next. One possibility is that the bromine radical reacts with the radical at the tertiary position. The other possibility is that the bromine radical reacts with the primary radical. So I end up getting two products because my reactants, my intermediate, is two different things. Someone asked earlier with the ketones. I formed two different ketones. Would we draw both of them or just one? And the answer was you would draw both structural isomers. If multiple structural isomers can form, all structural isomers form. Same thing here. These are simply structural isomers. I actually refer to these as 1,3 allylic isomers. Does that seem like a useful name to you? If you know you're going to form an allylic radical, allylic radicals lead to this 1,3 isomerism. So my radical halogenation gives me 1,3 allylic isomers. I invented it. I will admit to that. But I invented it because it's a useful way of describing the structural isomerism. Okay. Cool stuff. Yeah? I'm going to come back to this idea. I want you guys to think about which of these is more stable than the other. And how do you rank stability? Before that, though, let's look at this reaction. This was what type of reaction? Addition. And what am I adding across the pi bond? I actually don't need to do bromine here. I can, but it doesn't have to be bromine this time. I'm adding X. Am I adding a hydrogen? Where does it go? To the more substituted carbon. So I'm adding H and X. We already did that. I can't use just HX because I know how that story goes. This acid reacts with this base. This base forms a more substituted carbocation. That more substituted carbocation will rearrange. The nucleophilic attack will happen there. I need something different to happen this time. So I add a radical initiator. HX does not form radicals on its own like halogens do. So I use hydrogen peroxide, or really any peroxide. And we can abbreviate any peroxide as ROR. No, I'm just kidding. We don't call it that. ROOR. Any peroxide. Tert-butyl peroxide is not uncommon. Methyl peroxide. Hydrogen peroxide is by far the one we're all most familiar with. What is the role of hydrogen peroxide here? This is our radical initiator. All right, just because I'm erasing this doesn't mean I'm not going to come back to ask you about stability. So keep thinking about how could you compare the stability of those two products. All right, I want to show you this mechanism because I think it's cool. The first thing that happens here is the hydrogen peroxide splits into radicals in the sunlight. We form two equivalences of that hydrogen peroxide. I'm really just going to show you what happens with one equivalence. So the other equivalence is kind of unnecessary there. Once this radical is formed, now it can interact with our HX reagent. The oxygen radical takes the hydrogen, creates a radical with it, so in my first step, I've got this second equivalence of peroxide radical that is, it's going to go and replicate this whole process. In my second step, I form a byproduct of water and a halogen radical. what is this step? Initiation, propagation, or termination? Here is my initiation. No radicals become two radicals. One radical becomes a different radical. Propagation. From here, I introduce my alkene. The halogen radical reacts with the carbon radical, or with the carbon pi bond, to form a bond. And it will form a carbon radical on the most substituted carbon. That means the carbon with more carbon attached. I want to point out in the HX addition mechanism, we add hydrogen first, form a more stable carbocation, and then have the halide attack. Now we're doing it different. We add the halogen first and form a more stable carbon radical. Now let's get the hydrogen in. Here, I react with more HX, and my carbon radical forms a bond with the hydrogen, and the halogen forms a radical. The carbon radical bonds with the hydrogen and gives me my final product. Anti-Markovnikov HX addition. This thing is almost pretty, except my arrow goes in a weird spot. So I've drawn a few components here. There's this very important radical on the halogen, this very important radical on the carbon, and then the image here depicts that this is a chain reaction. It's a cyclic process. After that first halogen radical is formed, it reacts with one alkene, which reacts with another HX, which produces more X radical, which produces more carbon radical, which produces more halogen radical, over and over and over until everything is consumed. What type of radical step have I not demonstrated in this mechanism? No termination. There was never a termination step. Doesn't that seem a little strange? If I create radicals somewhere, shouldn't I terminate radicals somewhere? If I don't terminate radicals, when I finish this reaction in the lab, I'm just going to have free radicals hanging around, ready to react with something. So before I move on over to the alkynes, I would like you guys in groups look at all of the radical species that are formed in this reaction and predict 2 plausible termination products that could form. I can think of at least 5. I should be able to count higher though. I think it maybe is just 5. So group up. Work with the people around you. Predict 2 termination products. No termination products are shown. All radicals that form are fair game. Predict 2 termination products. What do you know about termination?
Freaking nothing, John.
That's not true. I saw you looking at your notes.
I'm looking at it. It doesn't mean anything to me.
What do you need for a termination step?
Another radical?
How many?
I need 2 radicals.
2 radicals. Great.
So what am I doing then?
Grab 2 radicals.
From the finished product?
No, because the finished product isn't a radical. So don't pick the alkene. Don't pick the anti-Markovnikov HX edition product. Don't pick HX and don't pick H2O and don't pick H2O2. Other than that, pick 2 radicals and terminate them. And then grab another 2. Show me 2 termination products.
I'm still lost. Where in this diagram am I pulling? Anywhere?
Yeah, how many radical types do you see?
There's the X radical on the top.
Yep.
And then the bond break.
Carbon radical on the bottom.
Uh-huh.
And the oxygen radical towards the very top. So there's 3 types of radicals. And you are not limited to just one equivalence of them. Remember, if you do this in the lab with a small amount of reagent, like 0.01 moles, you've got 6 times 10 to the 21 molecules. 6, I don't know, trillion, quadrillion molecules. So you've got 3 types of radicals. Pick any combination of any of them. Recognize that you've got a billion versions of each at any given time. What would happen if they terminated? I'll give you one, but it's not, you can't use it. Hydroxide radical, terminate to form hydrogen peroxide.
Okay.
So the reverse step is a termination.
So then it could reverse from here too? Like this radical could terminate?
Well, this was a propagation step.
Okay.
So this X radical won't go back to HX, but this X radical could get together with a hydroxide radical, could get together with a carbon radical, hydroxide radical, carbon radical and a second carbon radical, halogen radical and a second halogen radical. I think 5. It's actually a little bit more limited than you think. Do you guys get 2? You want to go for all 5?
I have not one clue what you're talking about. Me neither.
What is termination?
Because I thought you said that we're not supposed to use anything that we have, so when you're talking to him, so I didn't understand what you meant by that.
No, well, don't listen to what I said to him then.
Sorry.
Don't listen in part. Don't take just anything. In order to do termination, what do you need?
Radicals.
How many?
2.
2 radicals come together to give no radicals.
Yes.
So pick any combination of 2 radicals.
So it'd be like bromine.
Bromine radical and,
Another bromine radical.
sure, there you go. You've got 1 termination product.
So it would just be kind of like the one before where you're putting the bromine like on the tertiary and on the secondary.
Mm-hmm.
That's what I thought.
So that was a termination step before.
Yeah.
But recognize we're not getting our product by termination, right?
Yeah.
We're getting our product by a propagation step.
Propagation.
But termination is going to happen at some point.
So then wouldn't there be more than 3 steps to radical mechanisms? You have an other,
What is other?
what that is.
Initiation, propagation, 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 propagation. It's a cyclic. Oh man, thanks. It's a cyclic propagation step. That scared me almost as bad as Layla did last week. Yeah, wasn't that you when I turned around?
No, it wasn't. You were talking.
Oh, it was Annie.
Yeah.
Oh yeah. Great, great. Oh, you got 3. Awesome. Annie and Camilla, did you think of 2?
2 what?
2 termination products that could happen?
Yeah, the 2 bromies.
Okay, that's one.
Oh.
And show me it. Yup, 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 yup. All of those. I think that was the 5. Great work.
Is it these 3 and then?
And then the
Those
2
two.
like that and that.
These are not termination products. No, actually, when you look from the bottom, circling up clockwise, that's a propagation step. It's just that one of the byproducts of that propagation step is the major product.
I see.
But yeah, these are both termination steps, and then there's 3 others. Did you guys get some?
We were thinking the radical halogen at the top of the circle
Okay.
and the one at the bottom.
Yeah, the carbon radical.
Yeah, the 2 halogens. They change.
Good. That's one. What do you mean by real one?
If we, can those go back?
They can.
Okay.
Yep, that's one of the 5.
Okay. And what about what's happening here?
That's propagation.
Oh, that's not.
Because one radical reacts with a non-radical to form a new radical
Oh, that's forming that.
and a non-radical. Did you come up with any? Yeah. Yeah. All right. Let's go through them. One of the possibilities is that the hydroxide radicals recombine. The reverse of initiation is propagation. So I could reform my oxidizer. What did you say? So that's one of them. I could also take a peroxide radical and a halogen radical, and I could form a hypohalogenite acid. Hypohalogenous acid, which is a terrible word. So let's imagine that I was dealing with bromine or chlorine. These are how we'd actually write out their chemical formulas, but their structure is Br bonded to O bonded to H, Cl bonded to O bonded to H. That is hypobromous acid, hypochlorous acid. Those are possible products that could form by termination, would not be great, right? Because I was not planning on this being in acidic conditions other than HX. I wasn't looking for hypobromous acid. All right, some other combinations. Okay, sorry, those are all radical peroxide with radical halogen. I could also form radical peroxide with the carbon radical, which gives me the exact same product as, what is that functional group that we just formed? Or what is the relationship of those groups? You don't recognize it? Doesn't that look like halohydrin addition? X2 in water. It adds a halogen to the less substituted carbon. You guys aren't memorizing your reactions. You think this final is going to be easy. And actually the final is like just stuff like this, right? Stuff you've seen.
Do we get 2 pages of notes?
You get front and back on your notes sheet, but I'll tell you what, doesn't matter if you don't know what you're looking at. So this functional group is what you get by running X2 in water. You get the alcohol on the more substituted carbon even. This is the halohydrin addition product, despite the fact that I did not have X2 and I did not have water. It's a possible byproduct. Another possible byproduct is when the halogen radical and the carbon radical come together. What does this look like, the product? Halogenation. Great job. X2 addition. And then the last combination that I could have, oh, I did miss one. I could form a halogen radical with a halogen radical. So that's what? 1, 2, 3, 4, 5. Okay, so I was short. There are 6. The last one is 2 carbon radicals coming together and forming It is tough. I saw somebody drawing it out. Yeah, it's tough to draw, right? Actually, even just drawing it now, I had a hard time making sure that I had the right carbon chains. So how could you make that easier? Count your carbons, map your carbons, make sure that you're keeping track of all of the atoms all at once. So fun. All of these are possible byproducts. Some of them have to happen at some point. At the end of the day, all of the radicals are going to come together and terminate. So somewhere in your reaction, you're going to have these byproducts. Cool. All right, last reactions for the day. Let's take a look at our alkyne. What are we doing with the alkyne? Addition. A few more descriptors that we can add. You guys want to keep adding? Addition. We are adding halogens. So is it halogenation? Is that the type of addition reaction I'm doing? Am I adding X2? One of them adds X2. Well, X2 never adds them to the same carbons. Halogenation always adds them one to each carbon. What else am I adding across the pi bond? Am I? I am adding a hydrogen. So at one point, I'm not doing halogenation. I'm doing hydrohalogenation. I'm doing HX addition. And at one point, I've done one equivalence of HX. And at the other point, I've done 2 equivalences of HX. What else can you add to describe this HX addition? There's a term that is already on the board that would help in describing, comparing this from HX that we've already seen up above. Remember, I screwed up. We started the class with that. This is not just HX addition. Remember that guy from the 1800s? Yeah, I'm adding H and X anti-Markovnikov's rule. I'm adding hydrogen to the more substituted carbon, both times. So one time, I'll say HX, one equivalence with what? I need my radical initiator. I need a peroxide. do you appreciate the role that the peroxide is playing in this HX addition reaction? If there were no peroxide, the regiochemistry would be opposite. The hydrogens would add opposite of where they're adding. The peroxide is the only thing making that difference, and it's because the peroxide is making the radicals to change the way that H and X react with the alkene. So what could I add here? What would solve my reaction? What reagents do I need? And? Good. HX in excess, or 2 equivalences, and peroxide. Without peroxide, that is not the product you get. Correct? Can I get an amen?
Amen.
Wow. Lively group. All right. Now I've taken you through all of your reactions. So you have 6 minutes to solve that puzzle at the bottom. Sure, I could do it in 2. So what do you need to do? You need to fill in reagents across the bottom and then predict products across the top. That means you need to be able to recognize what change in functional group are you seeing. And then, based on reagents, what change in functional group do you expect to see? Okay, we've got more reactions Wednesday. Oh, I'm not going to get back to that stability thing until Wednesday. We ran out of time. But I am going to come back to the stability thing. Do you guys remember what alkenes to think about? Oh, man. I meant what products. Yeah, the 1,3 allylic isomers. I want you to think about the stability there because we'll talk about them on Wednesday. Why? And by first one, do you mean on the left? Why? Okay, no. That's not the reason for sure. We can talk about it Wednesday.
Say I have an A right now and I fail the final.
Yeah.
Bad would that affect my grade?
I think you can do that in your grade book better than I can. I have seen people fail my final and pass the class. Selena asked me what my pass rate was earlier.
Right now it's 0.
This semester, my pass rate is 0.
Oh, I was like, what?
Well, I have passed no students yet, so.
I've lost stars.
No, I mean, I guess I've never thought about it. And it varies. Okay, so a year ago, spring 25, I had 4 students that failed my class. Good question. Out of 23. What is 4 out of 23? It's almost 4 out of 24. So it's 1 in 6 students failed my class. And by failed, I mean got below a C.
So 82.
82. And then fall of last year, I had everyone got a C plus or higher. So no one failed my class. Yeah, I mean, I'm happy to show you the numbers. Summer was in the middle. Summer had 1 student that did not pass. And oftentimes, these are students that don't come to the final.
They just don't take it or just...
Did they just decide, I know I'm going to fail the class and I'm going to have to take it again, so I might
Yes.
not worry about it.
Which is literally, no shade, the worst possible thought process you can have. You cannot do worse than not showing up. I guarantee you, you will earn some credit on that exam just by sheer luck. So showing up didn't help you prepare for the next time you're going to have to do that exam anyways. You want to come back and take it from me again? Get the cheat. Like, come take it and figure out what it's going to feel like, and then you don't have to guess before you come in the second semester. It doesn't make any sense. So I guess my pass rate is variable, but it ranges from 80% to 100% pass rate.
Not bad. That's very good.
I don't credit myself for that, though. I credit the students. So
I think you should credit yourself for it.
I don't know how to do this. It doesn't make sense to me in my brain.
okay, well,
Is that horrible?
what am I changing about this?
Well, you're getting rid of a pi bond, so you're adding a hydrogen.
I'm adding a hydrogen.
Oh no, you're not.
Oh, what am I adding?
I have no idea.
So
Do I correct?
maybe draw in your hydrogens to prove it.
We have one here.
Good.
We have one here.
Not good.
Oh, we don't have one there. I can't
Correct.
count.
Good,
So
good,
we
good.
are adding a hydrogen.
Okay, draw in all of your hydrogens here too.
Okay. Oh shit.
Also, there was no halogen,
Yeah.
right? So
I know,
HBr is a guess because there is no halogen added. I need to add 2 hydrogens.
So I'm looking at this. I
Or
guess
you
I'm
could look at this too. There's a lot of things. These have alkynes, these have alkynes. So you
Are
just
these
need
the
to
ones
look.
That you did wrong? Or these ones that we filled out last class?
It's the same one that we filled out last class. And by wrong,
It was just.
yeah, like you can see that this was an internal
Yeah.
alkyne on a terminal alkyne example, and this was an internal example with a terminal alkyne.
Okay. Will you go over this next class if I?
Sure, sure, but keep working on it.
Yeah, I'm gonna keep working.
I want to see your answers next class.
Okay, I'll show you them.
Great.
I should probably fill this out.
Yeah, I'm not sure why you didn't.
I wasn't here last class.
Oh,
I was.
sorry. That's
So it's my bad.
that's my fault
So I'll fill that out.
for not
Thank you.
realizing that. You're welcome. Yeah, get to know those reaction maps because identifying what functional groups they make, identifying the patterns. Do you know what I haven't really given you guys is I recommend every semester to make a table of reactions. So that means on one column, describe the starting material, alkene, alkyne, dihalide, geminal dihalide, vicinal dihalide, whatever. And then in the middle, reagents that you can apply to it, and maybe some notes about it, like carbocation intermediate, halonium ring intermediate, backside attack, syn addition, anti-addition. And then on the last column, the functional group of the product made. Produces a less substituted alcohol, produces a syn-diol, produces a cis-alkene, a trans-alkene. It takes so long. No better way to spend time with the reagents and become familiar with them. So I cannot recommend it more. I did it myself when I started OChem 2 because I realized there were so many reactions that I did not remember. And then all of my classmates stole it from me. And that was when I don't know if I have it anymore. And quite honestly, it was so bad. In the years since I've told other people to do it, I've seen students do their own version. I did mine on Excel, and you could actually organize it alphabetically. I've seen students hand draw it. I've seen students do it on Microsoft Word and like edit things in. You guys have your iPads now, and you can just make like a note. Yeah. Yeah, it takes a long time. That is the time spent studying. If you're wondering, how do I study this material? Build a table of reactions. That way you'll see the differences, you'll see the connections. I'd be happy to look at it. Absolutely. Johnny, I hope so. I hope not. There you go. That's the plan. Yep. Take care, Jordan.